Right. Okay. Not long ago, Paris 2024, men's 100-meter freestyle. Won by an absolute mile in comparison. Pan Zhanli from China shattered the 100-meter freestyle record and for the first time in 100 years was more than a second ahead of the nearest competitor. Okay. The next day, he quoted to China Daily that we've been adopting a scientific underwater monitoring and analyzing system to review our techniques and strokes so that we could train better and more effectively. That's him. Karl Chalmers was a silver, and David Popovic from Russia was bronze. In the women's 800-meter freestyle, there's two swimmers that are pretty much household names here. Katie Ledecky from the USA, Ariana Titmus from Australia, and the lady that won third, Paige Madden. Nobody had ever heard of her before. A year before the Olympics, she was 19 seconds slower in this event. In 1 year, she removed 19 seconds in her 800-meter freestyle. That's 1.2 seconds a lap. Swimming has entered what many other sports has been doing for a while. They've entered the era of performance-enhancing devices. Okay, so this device is a product made here in Australia. I've been a part of this for the last couple of years, and it's been a pretty impressive product to work on. Very simple. It's a hand-worn sensor. It's got a pressure sensor on the palm, pressure sensor on the side of the hand, an IMU on the inside, and a battery. Pretty much all it does. Okay, so this talk is not about how to become a better swimmer, although if you're talking in coffee there probably could be some tips to pass around. But this is more how we use LabVIEW in the application of building this product, okay? And there's a little asterisk in there because there was a little assistance from AWS, but predominantly this is a LabVIEW project. So the final architecture of the system, I'll just walk you through how the system sort of is laid out in the back end. And it is very sort of AWS sort of focused, but I'll get into sort of the more LabVIEW related aspects of it quick afterwards. So each swimmer, when they're training, they have these handsets on, one on each hand. There's two CSV files that are generated inside the device, basic data logging. All right, a mobile app then sucks up those files, compresses it into a zip file, and basically just through an API call, posts that up into a cloud routine. So this is running on AWS EC2, which is just their application layer. Okay. That application layer then just takes that zip file and just transfers it into a data storage facility, AWS S3. And it also creates a message in what's called Amazon SQS, which is just their queue managing system. Okay, so that's all sitting there. And, more devices, people are swimming in different pools, people are swimming around the world, they're all logging. Data is just loading into this repository. At the end of the system, we have a Lightsail application, which is nothing more than just a virtual PC. It's a Windows machine just sitting on the cloud, and it's running a LabVIEW application, right? We call it our data processing server. That's constantly monitoring SQS, and every time a new job is posted, an application spins up, right? And it collects that zip file, pulls it in, processes the data, posts a new zip file, basically full of all the post-process data, and then just changes that message in the SQS system from being raw, ready to work, to completed. And that's all it does. Just sits there and just logs the file, or looks for the file, processes it on demand, and shuts down. So, some files will take a while to process, so they'll keep going, but it's just on demand. Spins up, spins down. Okay, and then from that, we get just basic information that we can relay to the swimmer. We can look at their stroke rates. We can look at how much pressure and force they're generating through their stroke, lap by lap. We can give them some layouts about how their hand path is moving, how they're moving through the water. We can show them how their hands are being consistent. So nice consistency with the left hand, maybe not so consistent with the right hand, okay? So the swimmers are starting to get this feedback. It's not real time, It's hard to look at real-time data while you're swimming, but this is good information. The processing of this takes just a couple of seconds. So by the time they've uploaded it from their handsets through their mobile device, they've dried off a bit, they're looking with their coach, that information is there and accessible. It's on either, they can look at it through a browser or they can look at it on their mobile app. Then they're back in the pool and they're trying to fix that consistency issue. So it's not real time, but for swimming world, it's probably about as close as you're going to get. All right, some force field diagrams, and then some charts that you can look at that are interactive, that you can sort of see where your power spikes were happening, whereabouts in the stroke that was coming from. So these are all just tools that that this device has, and there's a heap more information that we have. We just haven't been able to figure out how to visualize it. That's the biggest problem that I have with this project, is how to show this information to people that are not data scientists and how to make it meaningful. So there's a lot of work that we still have to do to really, crack under the surface and give that benefit to these people. But we are working with a lot of coaches. We were working with a lot of teams now have data science members as companions to the team. So Paige Madden at University of Virginia is partnered with Dr. Ken Ono, who's a PhD mathematician who supports the swim team. So it's getting pretty technical these days. Anyway, the objectives of this talk wasn't really to talk about swimming or necessarily this product, but really how LabVIEW is being deployed in non-conventional ways, right? So I've tested measurement, manufacturing pretty much my whole career. So this was a very different leap for us to take this project on and work in a consumer electronic version as LabVIEW developers. I'll show you how you can adapt this sort of architecture very easily to support just general test and measurement, and some lessons that we've learned along the way. So I always feel that you learn a lot more from your mistakes, or from mistakes that other people make. The reason why this is done in LabVIEW, well, because they came to us, and that's really all we know. It could have been done in many other different languages, but I think LabVIEW still is one of the best platforms for running this type of application, because at the start, you don't have a mobile app. You're not going to invest in developing a mobile app before you know your product works. You're not going to set up the AWS architecture and do the .NET programming for the front and back end management that you need, because that's a lot of time, right? With LabVIEW, you can, just like you do in the lab, you can go and you can prototype. So we had to prototype the system with 4 main components. One was the Bluetooth interface with the handset, data processing module, right? Process all the data that you absorb, visualize the data, and then develop that multi-channel server that can spin up and spin down on demand so that we can manage bulk loads of jobs that come through. So the first step was, let's do the BLE interface. Great. If you can't read that, you cannot use built-in LabVIEW Bluetooth with Bluetooth low energy. Okay, all the native Windows features for Bluetooth low energy don't exist. All right, there is a Bluetooth low energy toolkit available, but it's not that easy to use. You have to know a lot about Bluetooth specific commands and a lot of configuration issues. We couldn't get this running with this device. We could do some, but you have to do Windows enumeration and registrations, and it's just not there. So we had to put our tail between our legs for a little bit. We went to a firmware developer. He built us just a Windows application that we could call, and we just communicated to it through UDP. So spin it up, talk to it through UDP. It does all the Bluetooth black magic in the background. And for us now, it's a very simple interface. We can just call it, send it a command to do something, and then read the response. All right, nice and simple. But that was a bit of a learning lesson. We thought we'd be able to just jump in and Bluetooth our way through it. That didn't prove to be easy. So second one is just working with the handsets themselves. So inside the handsets, like I said, they're really simple devices. It's just a microsecond counter. I don't know why they didn't design it with a real-time clock. We're still having that discussion. But at least it has a counter. We've got MEMS pressure sensors on board, 2 of them. And we have an IMU data capture. So it's a Bosch version of one. So it has this fusion algorithm built into it where you can take your angular, or you can take your magnetometer inputs and your gyroscope, it fuses all that information together, and you get what's called quaternions as the output, which is basically your angular motion, right? Breaks it down for you on the spot, on the chip. Interestingly, these pressure sensors are incredibly photosensitive, right? If you swim outdoors and it hits a little bit of UV light, they saturate. They go completely ballistic for a little while, and you get absolutely crap coming out of it. All of our prototyping was done in the evenings in one of the Sydney pools. We didn't realize this until we did a live demo in Saudi Arabia during a World Triathlon event, and all the data was crap. Okay? Took a little bit of problem solving and some really obscure note in one of the data sheets that was from years past that said, oh yeah, don't use this in a high solar environment. Yeah, so that was pretty interesting. The other thing is the accelerometer, 8 Gs, that's a lot, right? Well, swimmers swim, Olympic sprinters, their hands are accelerating at over 12 G. That was a bit of an unexpected outcome as well. Thankfully, how these things actually run over is that they're binary, how they roll over in a binary way, we can actually restitch that back. So we can actually get almost 16 G. We can get 15 G out of these 8 G accelerometers. So just have to do a little bit of post-processing, but that caused a bit of issue. And then this one makes a lot of sense, but we didn't really sort of pick up until we were doing the prototyping, is that there's a lot of iron in a pool, and if you're using a magnetometer, don't. So we've actually had to disable the magnetometer within the devices, which means we can't really do good motion. It's not good for ocean swimming right now, but in a swimming pool, we can make a pretty good assumption that you're swimming straight in one direction or another. So the magnetometer becomes less of an issue. We'll have to create a new model of firmware if we want to run it with open water swimmers. Okay, so these are some of the things that we went through. And then the data processing, I'm not going to get too involved in that because that's just data processing. We do that a lot, I think, everyone here. It's standard things that we had to do, signal conditioning, a lot of spectral filtering done to clean up the data, a lot of resampling, integration of the accelerometer so we can go from acceleration to velocity to displacement. And there's a lot of tricks involved in getting that done right, so you can actually, your DC constant doesn't just absolutely blow out of proportion. And then once we get all that sort of signal processing done, then we can actually go and start reading the data and trying to figure out, how do we locate and isolate strokes, and where do they do their turns and all of that. So there's a lot of real sort of in-depth analysis that we do. Different strokes have different behaviors, right? So freestyle, butterfly, backstroke, really easy. The hand exits the water, enters the water. Those are two really good events that you can trigger off of. Breaststroke, sometimes it goes out of the water, sometimes it doesn't. So breaststroke is a real pain in the ass. We still don't have it quite right yet. The next thing was to sort of work on the visualizations, because ultimately this data has to go to an end user, and when we're working with coaches to show them prototypes, and this is what we're doing, we need to be able to plot that data in a way that's meaningful to them. LabVIEW is great for charts, but most people don't like line graphs or bar charts. That doesn't, it's not, when I was working with the business, they're not engineers, and when I showed them all these great line charts with power and time and stuff, that they just wanted pretty pictures. So this is where sort of LabVIEW did fall apart a little bit, because pretty pictures are not on the console. So we reverted to doing a lot of sort of 2D picture controls and trying to create our own little prototype versions of some of these visuals. Ideally, there's a couple of applications that we tried to embed into it. There are Java charts. We needed to get WebViewer 2 up and running inside of that, but at the time it just wasn't. We couldn't get that fully functional. I think it's a bit better now, but this was probably about 3 or 4 years ago. Anyway, so the thing is, we got all of this prototyping done. So we got basically the bones of the system up and running so that we could get data off of these handsets, get it onto a console, onto a tablet, and then show that at the pool edge to coaches and swimmers. And that really started driving a lot of interest. And then that's where the business really decided that they're going to take this to the next level and start investing in the mobile app, in the sort of the web architecture that's going to support this as a more consumer electronic product. And then from the multi-channel server, so this is something we had to build sort of as we were building this back-end application. It's pretty straightforward. There is a lot of technicality inside of it, in the guts of it, but at the surface of it, it really is just a LabVIEW application that's monitoring an SQS port, and every time a message comes up, it just calls a particular VI, opens it up with option 8, which is your reentrant clone, spins it up, and then itself, when its job is done, it just closes down and shuts down. All right. Some of the things that we did have to take into consideration is how many can we do, right? If we want this app to be really popular, if there's going to be swimmers all around the world uploading swims constantly into this portal, what's the limitation? How many parallel processing events can we create? Well, there is a limitation. In principle, you'd think that you could do hundreds of these things, but each of these zip files that's coming to us can get up to at least 20 megs in size. As we do the data processing and we go from acceleration and the handsets XYZ coordinates, then we have to convert that into the real world frame of reference, the data explodes inside. So that 20 megs can go up over 10 times larger quite easily. If the more laps they do, the more that can actually expand. All right. Plus, when we're creating the summary files, there's a lot more information that we generate out of that too. So Windows, when you're running a Windows executive, Windows does contain how much information or how much memory it allocates to you, and all of these modules do fall within that window. So we haven't yet been able to break out of that limitation. There's a few tricks that we probably could adopt, but this was our first cut at it. The other thing was when we're doing the processing, I sort of didn't really pay much attention, and I was just doing very quick lab work, running very large arrays through different structures. But when we had to do the parallel, when we were scaling up, we had to go back and really clean it up and really look at memory usage, because these 3 different structures manage memory in 3 very, very different ways. So that should have been done right at the first time. But sometimes quick and dirty wins, and then you have to go back and clean up. All right, so just going back and saying, okay, well, what did we learn from this? This is great, but I think that there are applications for everyone here as well, especially if you're doing remote work and just want to get some type of remote access to some of your data. It's really easy to replace those handsets with just a remote test system. You don't need an API layer. You don't need that .NET interface. There are built-in AWS tools that are available with LabVIEW, or a package that you can download that will allow you to very easily just connect, and you can post your raw data into the data storage. You can send a message to SQS, and then you can just build a very simple server that's just running there, and it's just basically pulling those messages and acting on them. It is a fairly straightforward concept. So I guess actually before we go to questions, one of the things I did have, do we have time? When I was talking to people while I was building this through the different communities, one of the things I was talking to about was resampling and sort of a strategy that I've been using for decades. I did it use this a lot back in the day, but doesn't seem to be sort of well understood or well known. And I'm surprised that it's not built in as one of the mathematical processes in LabVIEW. But if you ever have to do any resampling of your data, has anyone seen FFT resampling? No? Okay, well this is a very, very easy way to just resample your data without having to worry about cubic splines or linear interpretations or whatever. You just take your raw data that comes in, put it through an FFT, you get your spectral component of that data. So imagine, let's say I had a bit of noisy noisy sine wave coming in, looking at this chart, probably about like 10, 15 hertz, something like that. I'm sampling it at 50 hertz. All right, so that's an important thing. So you've got your raw data coming in, and what you want to do is, if you want to filter it, you can just apply any smooth passband. And sorry, I just sketched this up in the back there. So this is not. This should be nice and smooth, and it should be symmetrical and all that. So you apply your passband, and you can use any kind of passband that you want to do. You can have a notch filter, do whatever you want, take out your DC components. The important thing is that your passband is smooth, and it goes down to 0 in a very smooth way. All right, and then once you have your passband set nice and smooth at your endpoints, so at your, say, plus and negative 50 hertz, you just start padding it out with zeros. All right, so you extend that from 50 to 100 hertz with zeros, pass it back through an inverse FFT, and now you've got your data nice and resampled at a 100 hertz sampling rate. All right, no noise injected, nice and clean, and it's a lot faster than doing element by element type of interpretation. So this is a tool that I use all the time, and I think it's incredibly powerful. So if there's anything that I can pass on from this, is that. All right, so any questions?
Whilst Chris is making his way over, quick, maybe a comment for Eli. One of the things that I think on the feedback point of view, LabVIEW for phones would be a nice functionality. Can we push and deploy to phone targets in the future? That would be really handy for this sort of thing.
I mean, you can deploy a web browser interface with GWeb, right? Did you explore using GWeb at all for?
That's on my to-do list.
Okay.
It is, but for this we didn't. Yeah, we just didn't have the time. But a browser from maybe from the prototyping side, that would be okay. We wouldn't be able to access the Bluetooth on the device, right? We wouldn't be able to connect with any of the internal hardware. So pulling in memory storage, I don't know if we'd have access to that either. So it wouldn't be good for pulling and pushing through Bluetooth. The other thing is people won't go to a browser to then go to find an app. So it needs to be, it can be maybe a browser-based app if you can load in from an icon. But browser, this type of information on a browser wouldn't excite my clients to.
They all expect to have a phone that they connect directly to. Yeah, that makes sense. Yeah.
Hey, Neil, great presentation. In line with mine, I was just wondering what was the impetus for this? Where did it come from? What was the opportunity? Where did it?
Where did this technology come from? Or?
No, what was the impetus to make this technology? Was there a client? Was there someone yelling out, "I want to know more about my swimming"?
So it's a serendipitous story, I guess. We had a contact who we'd done work for before. He worked for New South Wales Institute of Sport, and a bunch of random projects have sort of come our way through that. And he had one that he said was a consumer electronics fitness device that he wants us to come and have a look at. And we were really focused on a couple of other projects, and we weren't going to take it. So we went to this meeting just to entertain them, and we were going to say, okay, well, these are the people that we'll recommend for doing this. And we were probably saying, like, we should probably send them off to like either a .NET programmer or a Python group, because consumer electronics really isn't where we should be. I have a background in swimming. I used to be a pretty decent competitive swimmer. And when we sat down and they showed that we have these devices, so they had bought the IP from a company that had tried to produce these and didn't succeed. So they had the design, they had the handset design, the electronics, but they had no data processing. They didn't have any models. They didn't have anything. So yeah, we're sitting there in the meeting, prepared to basically pawn this off. And I grabbed Kurt and said, we're taking this one. this one's going to be ours. So yeah, it's been a pretty interesting journey. But yeah, so it was someone else that came up with this, and there really wasn't a use case. But as a swimmer, when I was training, the most technical thing we had to train with was a bucket with a rope on it. And like, right, that was, or then we got like these like stretchy surgical tubing that we'd be resistance training, but that's about as technical as it got. And, you know, as a budding engineer growing up doing engineering and training, you know, I dreamt of things like this. So when I had this opportunity to work with these guys, it was, you know, something that I've just been dreaming of for years. Yeah.
Yeah, I was wondering, you were talking about not being able to do live feedback, obviously because you can't look at anything while you're swimming. Have you considered audio as a feedback method? Would that work with like bone conduction headphones perhaps that might work underwater so you could actually hear things?
The couple of challenges that we've come up with initially, and that's on the cards, right? We want to do, ultimately this device, like the market for this, Olympic swimming is great, but there's not that many Olympic swimmers globally, but there's a hell of a lot of triathletes, right? And triathletes have a tendency to spend a fair bit of money on their devices. So you get a device into the hands of a bunch of triathletes and you do well. Triathlon has a lot of competition and a lot of live coverage, and during the swim section, or during the bike session and the run session, they've got all these meters, and the bikes especially are broadcasting everything, and they've got live stats. And swimming, they basically have a bunch of commentators trying to, you know, sit there and tell them what they're doing. So if we can get this feeding data to the support boats and then that broadcasting back, that's definitely one of the end goals. A couple of challenges that we haven't investigated is, can we transmit Bluetooth real time through water, right? Because in swimming, your hands are only out of the water for less than 50% of the time. So it's finding, you know, in the air, can we broadcast and send enough information in that window, and a lot of error correction that has to come with that. To the swimmer itself, similar thing. Like, can we broadcast? Bluetooth does travel a little bit through water. Wi-Fi maybe a bit better. Wi-Fi Halo, possibly a little bit better. But we haven't gone too far into that.
Go to Chris.
Hello. You mentioned on the server side that there was a Windows limitation for memory on your application. Can you talk about what the actual limitation was?
Good question. This was not my body of work, this was Kurt's, so I can't defer that one off. But Windows, from what I understand, is when you run a LabVIEW executable, Windows will basically allocate to you a set amount of memory that you can't exceed, and if you exceed that, things crash. And we've seen it. The servers crashed on us many times because we've tried to run. This is 32. Oh, okay.
You just needed to run.
Okay, well then maybe I'll just rebuild in 64. Otherwise, does it unlimited then? Is that the?
No, it's not. But it's better managed.
It's better managed. Whoever's phone this is buzzing off. All right. Okay, well that's one.
64-bit would solve that problem.
I think I'll have to go back through the memory banks. I think there were some limitations on why we didn't do 64-bit, and it's some of the packages that we're using in. Yeah, there's packages inside either the Goop, not the Goop framework that we're using, or the Viper one that has got a dependency on a 32-bit application, I think. So see if I can overcome that. But thanks.
I mean, since we're on the tip section, on the DVR, have you tried on I think it's called catch and release, where you create a DVR, send a DVR on the queue, and then destroy on the other end? So I think, no, there you're just reading in parallel. Yeah. So this is a tip for people that are trying to deal with large data sets. I found that actually destroying the DVR gives you
it gives you the memory back, yeah. But if you need it, so I destroy it as soon as I don't need it anymore.
Yeah, so but the last value, so when you destroy it, it gives you the value that it has in. So basically what we would do is we would enqueue the DVR references, and instead of reading like that, we would just destroy it. And because when you destroy it, you get the reading. That's how we would manage, and then you don't get any data copy. That reading
is still in memory, though, isn't it? And this is a very large array.
So I was monitoring memory when we were doing it, and when we were doing it this way, it kept increasing because every time I was reading, I would get a data copy. But if I did what I just said about the creating and destroying every time, I would get the memory back. So
yeah, when you destroy that, you get the memory back. But if you need, but the what you get back is the array as well. So if you use that, you're using the memory locally of that array. I think
so we would have to check with R&D, but I was doing memory allocation assessment because we were doing LiDAR images, which were really big. And we were able to sustain sending them by doing what I just said. So it's just something worth looking into it, and it could be that it is application specific.
Yeah, I do kill the DVRs the moment I don't need them anymore. But the problem is I've got the original, and then I have to expand it at least 12 times over and then process each one of those and keep them live. So the moment I don't need them, I kill them, and that does bring me return a lot of memory.
And now we were doing the FFT like we were doing,
yeah.
And then just passing the FFT.
Yeah, same. Actually, I'm not doing that. That's a savings right there. Thank you.
It is a huge savings.
It is a huge savings.
How are you scaling this, Neil? Like, how are all the different users? Are you spinning up dozens or thousands, hundreds of these Lightsail instances? How does each user tap in? Like from the viewing data point, not from the sensor, from the other side.
So once the data is, go back to the. Once that processing application is completed, there's a summary file that gets stored in S3. And then the .NET there's a RDS, there's a database that will say, this is the swim ID and here's the processed data files. So when people look at their data, they're only calling, this process zip package. So the .NET will open that zip package, pull out the data for the particular lap that they're looking for, and then publish that. So the Lightsail is only being triggered when new swims are uploaded from the handsets.
Okay, so your coaches or swimmers aren't using the LabVIEW application. That's just running silently.
In the commercially deployed version, it's sitting silently in the cloud. Nobody even knows that there's LabVIEW anywhere nearby.
Okay.
But LabVIEW is intrinsic in the development, in the prototyping.
So the end user gets the process zip file that they can access, and that has all the information they need. And
that through the portal. And I can show you what the actual web interface looks like, or the mobile app. But yeah, they're just pulling that post-process data that is basically this bar chart and a couple of other charts.
The portal. Okay, that's the bit I was missing. Thank you.
Yeah, I didn't show you the front end side of that.
Sorry. Can you scale this up to other sports as well, other than swimming?
Anything, yeah. It's just as long as you can process the data and get whatever relevant information from that data, that this is completely agnostic to swimming.
Like you said, there's a lot more devices on the other sports.
Yeah. So all the other sports, all terrestrial sports have already a saturation of devices. Cycles have ridiculous amount of. You're a cyclist, aren't you? Yeah. There has to be.
Irish road bowling.
Okay, we'll get into that. But even rowing, rowing is all sensors everywhere on the oars and on the seats and stuff. It's swimming was sort of the last spot for I think for human sport.
Any other questions in the room?
Okay.
Thanks, Phil.